Just to mention here, you can also start Zephyr with Remoteproc from Linux from U-boot. So they can start together. But yeah, I don't have an idea right now on how to start it from Linux to start from Zephyr. Right. They can start together, like from U-boot of Linux. You can with Remoteproc, you can start the Zephyr core.
I guess it would be interesting to see like maybe you can have like an intermediary where you just have like U-boot like just sit there, and it's just waiting for like the Remoteproc from the Zephyr side to say like, okay, now boot, right? Because the firmware is already like it's there, right? It's resident on the flash. So okay, U-boot is just sitting there waiting for and then like once Linux boots, like okay, the Zephyr side can query, like send a message and get a message back to see if it's successfully booted or not. Yeah. So this is the next iteration in that sort of kind of development process. I try to claim to be an FPGA engineer, but like I still stick to the embedded software side. So just a quick agenda for today's talk. We're going to go over motivation behind what we're doing. So if you want to sign up for it, you're welcome to, and you can find that on my website as well. So just a quick kind of summary about the motivation behind OpenAMP. So we have nowadays a lot of heterogeneous multiprocessor systems, and traditionally they have been on distinct silicon dice. So the OT process for the MCU, for the Cortex-M itself, for example. So that kind of framework or that kind of mentality led to the genesis of like this OpenAMP framework, which you can find a lot of documentation on as a starting point on the GitHub repo. There's multiple components to it, and we'll get into in a little bit. We have, of course, the OpenAMP library. And so the two main components of it are the Remoteproc and the RP message. They're the core building blocks of this particular library. So these two components actually were originally committed to the Linux kernel by TI. So the motivation for these implementations were essentially allowing communication from between Linux and TI RTOS, or what was then known as sysbio. So that was kind of the original motivation for TI starting this framework, and then it got picked up by OpenAMP, which turned into kind of this overall project and organization. And then they expanded what TI's work, what TI started, into a much more comprehensive and extensive library and framework. So this is kind of the overall motivation behind OpenAMP in general. So we have essentially a single kind of piece of memory that's essentially shared across, let's say, the different cores. We have the Linux and their application that's running on the Core A, the Cortex A, for example, and then we have, let's say, the RTOS and the bare metal implementations on the different Cortex-M processes, right? So essentially, it's like this is all one big piece of silicon, and we're just kind of we have to just be cognizant of how the different memories are distributed. So let's kind of dig into some of the actual applications and processes that are responsible or that kind of build up OpenAMP. So first we have Remoteproc, and what that's responsible for is to start marshalling, kind of writing or setting up the firmware on the MCU, for example. So one of the steps that it does is, one of the first things that it does is parses the L file, and so it's important for it to do that. So it's assured that it has the appropriate memory segments that are to be loaded. And this is going to be kind of important later on as how this ties into Zephyr. And so it loads the remote processor firmware, and then it also starts, essentially just kicks the MCU to kind of get it going. And then we have RP message, which is the actual communication mechanism between. So once you use Remoteproc to basically load the firmware and get it going on the Cortex-M, for example, RP message comes along, and you can use that to essentially communicate between, let's say, your Cortex-A MPU and your Cortex-M MCU. And that's a very well-defined format on how this message exchange occurs. So, you have this standard framework to communicate between these different cores. Two more kind of implementations of these overall mechanisms is, one is virt.io, so it kind of abstracts out the interprocess communication. And again, it uses kind of the shared memory region between the processors. And then we have metal, which is essentially the abstraction of the underlying OS primitives that OpenAMP uses to ensure, like, you know, that all of the communication between your different processors are efficient, they're not kind of just hogging, like they're not just inefficiently implemented. So kind of just looking at, now that we have kind of an overview of OpenAMP in general, we have Remoteproc, we have RP message, and then we have Metal. So just kind of a quick overview of where they reside within Zephyr itself. So OpenAMP itself is an external repo that's part of the modules directory in Zephyr. And then so we have the Zephyr implementation of OpenAMP, which is essentially this resource table, which we'll get into a little bit. And then there's an example that I use as my starting point in Zephyr, which is under sample subsys IPC OpenAMP resource table. So that was kind of the starting point that I used for kind of this particular effort. And these are the relevant kconfig options. So config IPM is kind of enables the OpenAMP, the interprocessor kind of communication subsystem within the IPC subsystem within Zephyr. Config OpenAMP basically compiles the OpenAMP subsystem, and then the resource table config options essentially enable kind of this resource table, again, because that's one of the things that Remoteproc uses, is it verifies that your ELF file has that resource table entry to make sure that, you know, there is actually shared communication, that the MCU is aware that, oh, they're like what that shared resource is, so that it can communicate between the MPU and the MCU. So that's one of the first things that Remoteproc does, is when you actually, and we'll see how that loading process works, is very straightforward. One of the first things that there's like a kernel module on the Linux side that kind of checks and parses the ELF file to make sure that it meets certain requirements. If it doesn't, it kind of throws errors, but if it does, it essentially just starts the process of loading that into the MCU. And so one of the things that it does is it checks to make sure that this resource table entry is present in your ELF file. And then also, we need to make sure that, because we're kind of the slave in this, as part of the MCU, we need to disable the option to make sure that we're not the master in the OpenAMP configuration, because it defaults to a yes in Zephyr kconfig. And this is basically an example, in that same example that I referenced earlier. This is just the overlay for the board file that they're using, which is a STM32 part. And you know, this is going to be useful later on. So again, we can see that we defined two things. We defined the IPC shared memory, right? We referenced that to a region of memory that's defined by the vendor, that is shared between the MCU and the MPU. And then the IPC itself is a construct that we can kind of create and use that for the communication itself. And then we can use, like, which is typical in a lot of these multiprocessor systems, is we have this kind of mailbox configuration. So this was kind of the basis for what I did as part of this development effort. So kind of talking about the actual specifics of this project, and again, like I did it on different pieces of hardware, because the hardware that was originally intended for the project was custom and proprietary. So I wanted to kind of see what I needed to do essentially to use like a commonly available like development board, and then see how that kind of takes me, how that progresses. So this was essentially, it's the same sort of Xilinx product, but just on a different board by a different vendor. It's a Digilent Genesis ZU. It has a Zynq MP sock, so that's essentially a quad-core Cortex-A, and then a dual-core Cortex-R. So it's not the Cortex-M that we saw earlier in the earlier silicons. This is a Cortex-R, which is meant for kind of real-time operations. So this is just a block diagram of the specific controllers within the MP sock. So essentially, we have the Linux side that's going to be running on our Cortex-A, and then we have our Zephyr is going to be actually running on the zeroth kind of Cortex-R MCU. And then we need to define, again, like they call it an IPI within Xilinx land, like that's essentially going to be our IPC communication. And then the shared memory is what we define as the shared memory for the IPC as well, right? So we're going to need to define those in our device tree. This is, again, just kind of a block diagram showing from Xilinx's website like how this sort of implementation works. So on the Linux side, we have essentially the same sort of OpenAMP infrastructure, RProc and RP message, and then underneath that is the virt.io kind of implementation to serve as the implementation of these two constructs. And then similarly on the Zephyr side, we're going to have kind of the same sort of thing. We have RP message, and then because Remoteproc is only on the Linux side, we don't have that on the Zephyr side. And then the virt.io is simply going to implement the RP message on the Zephyr side. So the goal is essentially we're going to create a Zephyr binary that's going to be resident, that's targeted for the R5, and it's going to be resident on the A53 RFS. We're going to load the firmware from the Pedal Linux side, and then we're going to start it, and then essentially we're going to send a message from Linux to Zephyr, and the idea is that we should, the expectation is that we should get that message back on the Linux side as well. Okay. So how did I get started with this? So there's not a Digilent board in Zephyr at the moment, so I tried to find something that was close enough, and I found the Korea KV260 R5 board that is kind of present in Zephyr, and I use that as a starting point. And the first thing that I did was I wanted to make sure that my pinouts were correct, my clock configurations were correct, right? And I just got Blinky working, essentially. That's generally when I want to use a new board or new kind of processor that's based on a newer board, that's usually kind of the first step that I do is just get Blinky working. And it's not kind of sufficient to just like, yeah, you know, like just eyeball it and see that it's blinking like at 1 second. Like you actually have to kind of generally like hook up like a scope and see, okay, you know, maybe 110 milliseconds, 100 milliseconds, et cetera. That gives you confidence that, okay, your clock configurations are correct. The next step is just to get like UART working. So if you have Hello World, that's higher confidence that your clock configurations are working because UART is a little bit more sensitive to kind of clock configurations, et cetera. So if your clock is off, you might be getting just garbled, data that's coming out of your UART. And so, part of this exercise also was, and we'll see later on, is like getting the Xilinx kind of tools like Vitis working with kind of Zephyr. So, typical flow is we have kind of debuggers, debugger configurations that are part of Zephyr, and you can use command line or you can use like Nordic Connect, and then you have like a debugger built in. This is a little bit different because there's no native kind of Vitis support in Zephyr, so kind of had to like get some like janky setup going, and we'll kind of get to that, like what that looked like a little bit, and then what the next steps are for that. And of course, the last step is to test, right? So once we have that working, we needed to or before this is once you have Blinky working, then we needed to make the appropriate configuration and modifications to get that working with OpenAMP, along with kind of the Echo example that's in kind of the Zephyr samples. So on the Pedal Linux side, it was pretty straightforward. We go through the Pedal Linux configuration. It's not the kind of focus of this talk. So all we need to do is enable the Remoteproc kernel modules and drivers so that we have that capability in Linux essentially. And then this is something that I needed to do, is to create the recipe in Pedal Linux to add the Zephyr binary. So the process was I'd build the binary. It was pretty manual. Like you build the binary, the Zephyr binary, and then you kind of plop it down into your RFS or your Pedal Linux build, and then create your RFS and then load that on the Xilinx side, and then kind of get going from there. So maybe there's opportunity here to kind of make this more integrated so that you have like a automated process where you can just build the Zephyr binary and then it kicks off like a Pedal Linux build to kind of embed that essentially. And then you don't have to like do more manual steps. And like I said, like this was an important step to help me kind of debug issues that I was running into, is to use Vitis as a debugger. And so it was pretty manual. Like I had to copy over a lot of the source files. There's like a bunch of different configuration steps in Vitis itself to kind of let it know like where the source files were, like where they were, how to set up the debugger itself, and then kind of reconcile the symbols within the binary within the source files. But, like it was painful, but at the end of the day, I got like a pretty nice debugger where I could debug Zephyr code on a Xilinx kind of FPGA through their native kind of debugger, which is pretty nice. So kind of, let's say, so once things kind of started working well through the debugger. Like how do we actually kind of load the binary and get it going, right? So it's pretty simple, right? You just, because the binary is resident on like a known path in our RFS, you just tell it like the file name without the extension. You just echo that to the sysfs entry, and then you just echo start, and it kind of kicks the tires. And then once, and it was pretty fascinating because I had the Vitis debugger set up, I could just set a breakpoint, and then like once I hit start, you could actually see like the breakpoint in main kind of kicking, like, okay, this is actually kind of working. So it's pretty nice. So kind of pivoting into some of the common issues that I encountered and could kind of share some of the lessons learned with you. One of the first things that usually that did happen is just issues in loading and starting the firmware. So the kernel module itself, like again, if you don't have the appropriate entries in your ELF file, it's going to throw an error. And one of the biggest reasons was you need to actually define this config option, like config OpenAMP resource table, is because it compiles essentially like resource table.c has an explicit entry for the resource table within your linker essentially. So then within your linker script, and then it adds that to your final binary. So that's kind of the one common issue that that I think a lot of people kind of run into. That's important to kind of make sure that's part of your board configuration. The other thing was, and I see this kind of common as well, is like, okay, you got the like your binary is running, right? You can use different mechanisms to confirm that your Zephyr binary is running, but now when you start to communicate from the Linux to the Zephyr side, you get a seg fault, right? So like, why does that happen? So a couple of things to make sure that you're doing before, to make sure that you're actually doing to ensure kind of this doesn't happen. One is your IPC connected to the mailbox in your DTS, right? So sometimes that's not necessarily like a seg fault, it's just like nothing happens, right? Like I have a breakpoint where I have a callback set for when I get the message, but it never triggers, right? Well, do you have your mailbox set up to Zephyr IPC to make sure that communication is being received on the Zephyr side? You have to make sure that your SRAM, because in the normal kind of KV260 DTS file, the SRAM is not, it assumes like there is no other coprocessor. It just assumes that microcontroller is just by itself. And so you have to kind of update it to make sure that you're pointing it to the right memory location, to actually point it to the RAM is in the right kind of shared memory location that we saw kind of earlier. And then finally, did you make sure that your shared memory node is actually connected to your SRAM? So these are kind of the general 3 things that we need to make sure to ensure that we have kind of a successful communication between the multiple processors. So this is kind of like a detailed example of like what that looks like. So this RPU0 IPI is the interface, and then between like the IPC interface, which Xilinx calls IPI. And then here we can see like the mailbox that's essentially the entry between, or the communication mechanism between the Cortex-A processor and the Cortex-M0. So this is the 0th MCU. And so all we need to do essentially is make sure that we enable that. And then in our overlay file, just ensure that we're setting this Zephyr IPC node entry to a reference to this particular mailbox. And then the other thing, like I said, is make sure that your SRAM location is correct. So the left is actually from Xilinx's kind of example on how they do OpenAMP with FreeRTOS. So essentially, we need to make sure that we specify these RAM locations in our Zephyr DTS and update that node appropriately. And then again, we have to make sure that our Zephyr IPC shared memory node points to the appropriate reference to like our SRAM node. And then, the idea is that once you have these 3 components kind of all correctly configured, then you should have communication between the different coprocessors that are resident on your silicon and on your system. So some of the next steps, of course, and I'm terrible at this, is to upstream, right? So add the board to like Zephyr, make sure it's there. You know, it's a slight variation on the KV260, but again, I think having as much board support in Zephyr is pretty valuable. And then, like I said, you know, I think it would be helpful for me to document the steps to get Vitis working with Zephyr, because I think that could be pretty powerful tool for somebody else that's kind of using Zephyr with Xilinx products to be able to kind of step through using Vitis. So I think I have about...
if I remember correctly, with STM32MP1, for instance, there were some concerns about OpenAMP and RP message throughput from the A7 to the M4. I think someone benchmarked it around 100K per second because it wasn't zero copy. You're always, you know, managing this ring of shared buffers in SRAM. So if you want to do like zero copy transfers, is there some improvements that have happened in how that can be handled in OpenAMP, or is it better to just go below that and manage shared memory and signaling yourself?
Yeah, I'm not sure. Yeah, I haven't, like, this was kind of just a purely functional test. Like, I didn't actually see like, okay, what the performance looked like. But yeah, I mean, it would be nice to see like where that limitation, if it like where that like non-zero copy occurs across a different memory, and then see like, hey, you know, is there an opportunity to just improve OpenAMP, and then, you know, maybe like Zephyr could be leading the way to improve like OpenAMP's performance essentially. So yeah, that's a good question.
So now you're booting the R core from the A core. You played around with the master function, so you first start Zephyr and then Zephyr starts your Linux kernel. So you have like a 1 second boot.
That's a good point, but like, how I guess so? You're assuming like that the firmware is like, where would the Linux firmware and like RFS be resident? Like, you would have to kind of figure out a way to, like, it would be resident in Flash, right? And then you would have to instruct like the Cortex Ada, like, or would you, like, I guess I don't follow like what that.
I'm implementing OpenAMP with Zephyr on the 9.5, IMX
Okay.
9.5. So there we can use the boot fuses to launch Zephyr from the QSpy.
Right.
And then the idea is to implement Remoteproc the other way around. But as a stopgap right now, we're just going to boot first Linux and then the other way around. But the notion that you have this fast RTOS booting, doing your pmuxing, and then like 10 seconds, 20 seconds later, whatever, depends on your Linux, right? That comes up later then.
Right. I guess I'm just curious, like, how, like, are you triggering the Linux boot from Zephyr?
Well,
or is that the idea?
That's the idea.
Like,
There's now is a different bare metal method for it, but I was just curious because I now saw this master. It's like, oh, hey, cool. Maybe someone made that already.
No. I mean, like one of the things that like I was thinking about is like, okay, like if we kind of go back to like the robot, right, that I showed earlier, like one of the things like, okay, while Linux is booting, you could still kind of use the display interface to have Zephyr kind of display like a simple message so that, okay, while Linux is still booting, you have something to kind of inform the user, like, hey, like what's going on. But yeah, that'd be interesting to see like how does, because I mean, if you're on the same silicon, right, like you're getting power for both, right? So like how do you kind of stage it so that Linux boots after kind of Zephyr? So, yeah. And what would be, just out of curiosity, like where do you see that being like valuable?
So we're looking also at robotics. So the idea is that Linux is quality managed from safety critical perspective. So that can die, that can reset, that can crash. So, and then the control loop is running on the Zephyr side. So especially that robot, it will trip over. If you're going to use Linux, if you have Zephyr, you have uptime, it shouldn't fall over. Just you have power, you can run your safety critical or control loops.
Got it. Well, yeah, cool.
Yeah, I've got a slight question or comment on OpenAMP, the protocol there. Are the messages fixed size? I mean, I think they are.
I think they're well defined. Yeah.
Yeah, and so one of the challenges that we've run into is like it's like you want a version of it that allows you to have flexible sizes for things like a network coprocessor sitting off on the that you're using OpenAMP to discuss. And so we end up, I'm saying we, my company, we end up with a custom version that's kind of close. And I'm not exactly sure why we didn't try to engage with the OpenAMP community to see if we can't get that up there And I'm not even remotely familiar with the underlying change they did there, but it was dynamic versus fixed was a problem for certain types of applications.
Yeah, I had the same issue when I was talking yesterday about VirtIO, MMIO, that when you have that running underneath, you can run API message on that, but that's fixed size and small units. But then next to it, you can expose a VirtIO network interface, for example. And then you use shared memory and next to API message instead of on API message.